Okay. Now, let's talk about the total incoming power. We have seen that there are two ways of entering power into the body. One is the mechanical power, the other is the thermal power. Okay? The first part, till here, in virtue of the theorem of the expended power, is equal to the variation per unit of time of the kinetic energy plus the stress power. That's what we have seen. The second part is what we have just recently seen. We have just seen that this is due to the heat sources and the convective flux. Okay? So it's different ways in which we can enter power, that is work per unit of time, into the body. Some variation of kinetic energy, some stress power, this is the mechanical power, the sources, and the heat conduction. Okay? That's the summary. Okay. So let's talk about dissipation. Now, so far we have talked about how we enter work per unit of time into the medium. Okay? Let's now talk about what is done with this work. Okay? So, we define the stored mechanical power. So I anticipate that all this work that we enter via mechanical or via thermal power into the continuum medium is going to be, part of this work is going to be, so to speak, stored or saved in the body so that eventually it can be returned. Okay? I will put some examples about that. But there is another part which is lost, and that is the concept of dissipation. Okay? So I anticipate that dissipation is that part of the power that we enter into the body that is not stored, that is lost. Okay? And that is a very important concept in thermodynamics, in thermodynamics of continuum mediums, and particularly in nonlinear solid mechanics. Okay, what is the stored energy? Well, we assume that, of course, the energy that I enter into the medium, it's something that can be stored into two components, so to speak. One is the kinetic energy. The kinetic energy is something that is an exact differential, okay? So it's a state, in thermodynamics we call that a state function, and then that's something that can be returned. I can diminish the kinetic energy and I return something at this cost, as I did in the example of the book, okay? And then there is another part that we define in terms of something which is a new word for you. Please pay attention to that. It's called the free energy, or the Helmholtz free energy. This Helmholtz, this T is not correct, by the way. This Helmholtz energy is defined in terms of phi, which is a function again of the space and time, which is the stored mechanical energy per unit of volume. So this is the kinetic energy. We assume that the stored energy is made of the kinetical energy and the mechanical energy, stored energy. And the description of the stored energy is going to be done on the basis of the Helmholtz energy, which is a function of space and time. Per unit of its a specific stored energy, because it's given per unit of mass. If I want to have it in terms of volume, I have to multiply that in terms of the density, and then the product is the density of free energy, which is the quantity of mechanical energy per unit of volume. Okay? If I now make the integral of the stored mechanical energy per unit of volume multiplied by the volume, then is that term here, that integral here, represents the total amount of the stored energy. Okay? And this differential means the variation per unit of time of the stored energy. So the stored mechanical power is the variation per unit of time of the stored energy, which is made of the stored mechanical energy plus the stored mechanical energy, which in turn, That one is described in terms of the velocity, and that one is described in terms of another entity that is the free energy. Okay? So that is our paradigm, it's our assumption. Okay? Okay. So if we quantify the stored energy, and this way, the variation period of time of the kinetic energy plus the variation period of time of the stored mechanical energy, what we describe by this B, then we define the dissipation, as I said before, as I anticipated. The dissipation is that part of the external work per unit of time of the power, that part of the power, which is not the stored power. So is the difference of the total mechanical energy. Well, of course, there are sorry, I anticipated something. We can talk of two different dissipations. If I consider the mechanical part of the power, that mechanical part of the power is part of it is stored, which is that, and part of it is dissipated, it's lost. Okay? So we can talk about the mechanical dissipation, which we'll denote by D, which is the difference of the entering mechanical power. I recall that this was in virtue of the theorem of expanded power, the variation per unit of time of the kinetic energy plus the P sigma, which stands for the stress power, minus the stored power, mechanical power, which is in turn again the dk dt plus the nu dt. And then we see that this term cancels. So final dissipation, which is understood physically as this, no? that part of the power, mechanical power, which is not stored. Okay? That is the definition of dissipation in words. Then in symbols, it can be described of that. This term plus this term minus this term plus this term, this and this cancel. So this is the stress power, which is that, and that term here. So finally, the dissipation can be written as the integral of the volume of the stresses times the rate of the strains, which is the stress power, minus the derivative of that, which can be introduced in virtue of some theorems as rho phi dot. This is that derivative, which is the variation of the stored energy per unit of volume. Okay? So this is the dissipation, mechanical dissipation. Look, so we have talked about mechanical dissipation as the difference of the mechanical power minus the stored mechanical power, okay? Which again can be written as that. Then the total entering mechanical power is equal to the part that is stored plus the part that is dissipated, okay? Which is a sketch here. I have a mechanical power, okay? And then the mechanical power is invested into a variation of the kinetic energy and a variation of the stored energy, okay? That eventually can be returned, plus something that won't be returned, the dissipation. Okay, that's the concept of mechanical dissipation. That part of this which is not stored, that cannot be returned. Okay, that part here. And it can be written, as we saw before, in that formula, in terms of the stress power and this new concept, which is the free energy or the half of energy, which plays a fundamental role in the theory of constitutive equations. Free energy, we call that. Of course, in the same way that we talk about mechanical dissipation, we could talk about thermal dissipation too. And that is a more complex aspect, because talking about thermal dissipation involves talking about something that is difficult to understand for us, regular people, so to speak, which is entropy. I say also to my students, why entropy is not familiar with us? Because our senses are not capable to to perceive the entropy. We have senses which are able to see light, So light is something that we can understand. It's noise. Heat, we can see heat. We can notice heat. We can see this is colder than this, or heater than this, hotter than this. So then temperature, light, sound are something that we are familiar with because we can notice them with our, because we can perceive them with our senses. Entropy is not. But that doesn't mean it doesn't exist. And that's the, so to speak, the magic of the thermodynamic, okay? So, entropy, so to speak, is the amount of temperature, no, the amount of heat per unit of absolute temperature in the body. That's a definition that you can do. What is this? Well, no, you cannot. I mean, it's like if you say it's a cow. I mean, flying. Okay, that's something that, I mean, you can believe me or not, but it is. Okay, so that's the definition of entropy. Okay, we are going to use that. We are going to go deeper on that. Just believe me that then rho as the dissipation, the thermal dissipation. So that part of the heat power that is dissipated can be expressed in that way, minus the integral on the volume of the entropy, which is a function of a space of time, as temperature is, or as whatever of this is, times theta stands for the absolute temperature, theta dot then for the rate per unit of time, the variation per unit of time of the absolute temperature, and rho. Okay? This is what is called the specific entropy. Rho s is the density of entropy, and that is the expression of the thermal dissipation. So finally, if you look at that body, and I consider that I can enter power into it by two ways. One is mechanical power, the other is thermal power. Second, that as a consequence, part of this work per unit of time, can be retrieved later on, can be returned later on, and part is not. And this part, what is lost, is what we call dissipation, and there is a mechanical dissipation, which is expressed this way, and a thermal dissipation, which is expressed this way. So the total dissipation into the body is the sum of this plus this, and that's what we have here. And then there is a magic theorem that is really, for me, it's exciting to see how people could postulate it, which is the second principle of thermodynamics. Now maybe we can get acquainted with that, see that something, maybe, I don't know if you can perceive that, but the postulate is that dissipation, so that energy that is lost forever, okay? So you can never retrieve them. It's always greater than zero. That's the second principle of thermodynamics in continuum mechanics, okay? It says that, as the definition, that amount here expresses the quantity, that power that is lost, and this quantity is always greater than zero. Dissipation cannot be never smaller than zero. That means that somehow, what about if dissipation was smaller than zero? We would get energy from nothing, okay? And that's something that, I mean, it could happen maybe in our universe, but in our universe there is no experiment confirming that we can get energy from nothing. At most, sometimes we lose energy, but we never get energy for free, okay? So that is what it's saying here. In a volume of a continuum medium, the dissipation expressed in that way is greater than zero. And there is something here that is important too. That means in all part of the body, you know that if I consider that as a continuum medium, every page of this book is a continuum medium too, okay? So this stands for the full book, but for every page considered as an independent continuum medium. And for every particle of this page. That means for every subset of the continuum medium. For every subset of the continuum medium. as small as you want. Okay, that's something. If we don't include that, then we cannot extract consequences of this. But the second principle of thermodynamics says that dissipation is greater or equal to 0, never negative, for any continuum medium and any subset of the continuum medium. Okay? And just to finish, this is what we have arrived to. We have a continuum medium at time t. Dissipation is a function of t. That dissipation, well, of course, we define now something that can be defined as the density of dissipation. So the dissipation for unit of volume. This calligraphic d, then integrated of the volume, is the total dissipation of the body. Okay? So this density of dissipation, which is a function of xt, integrated of the volume, is equal to the expression we have seen before. These two terms refer to the mechanical dissipation, this term here refer to the thermal dissipation, and they have to be greater than 0 for every volume, subset of the volume at this time t and at all times t. Maybe I forgot to say that. I should have added here for all times t. At all time, at all point of the space. Look, what is the consequence of that? That then, that implies that I could apply that. If I apply that to a single particle, that means that this part here is equal to that part here at all points, at all particles of x. This is called, in continuum mechanics, the process of localization. Many of the conservation principles, if you look or you recall the way they were deduced for you at the class, you will see that they were postulated with all that. So they can give from an integral equation to a pointwise equation, which is that. What would it say is that this term is equal to this term. So at every point of B, this is equal to this and have to be greater than 0 for all points and for all times. And this is what we call the local form of the second principle of thermodynamics. That says the following. The density of dissipation can be expressed in that way. Look, no integral is now appearing. And has to be greater or equal to 0 at all times and at all points of the space. Okay? In other words, every physical process not fulfilling that can be imagined, but it cannot happen in our universe. Maybe in other universes, but not in our. Okay? That discriminates that greater or equal that says, okay, imagine a process, compute the dissipation, compute that, and then compute this result. If it's greater than 0, it can happen, or equal to 0. But if it's smaller than 0, this can never happen. That is the genius of the second principle of thermodynamics. It's something that discriminates what is feasible from what is unfeasible. Okay? And we are using to use that crucially in our thermodynamic framework for derivation of constitutive modeling. So this is the starting point. Okay? Then, and just to finish, there are some manipulation of these equations. For instance, normally we define something that is the internal energy or the total stored energy. Phi is the mechanical stored energy, S theta is the thermal stored energy, and then we define U equal phi plus S theta. And then we can, this is the internal energy, which is defined that, it's definition. Of course, if I have this, I can define this, it's definition, okay? And on the basis of this definition, I can just take time derivative, U dot equal phi dot, plus the derivative of time with respect to that, which is the first times the derivative of the second, plus the derivative of the first times the second. Okay? And then rearranging terms, passing this term to the other side, we find that phi dot plus S theta dot is equal U dot minus theta S dot. It's just an algebraic equation. And then the expression of dissipation that in terms of the free energy was given like that, then we can replace this equation here and give it like that. This term minus rho phi dot plus s theta dot is u dot minus theta s dot. And this term remains the same. And that's an alternative formulation of the second principle of thermodynamics, which is called also the Clausius-Planck inequality for thermomechanical problems. Okay? And this is classical ways of expressing all this long story I've been spending 1.5 hours to explain you about what is work, what is stored energy, and what is dissipation, and what second principle of thermodynamics says about this dissipation, that is always positive, and how does it translate into an equation. That's an equation that has to be a differential equation, because differential with respect to time. Here there are differentials, because it is differential with respect to space or velocities. So that's a differential equation, but it's a differential inequation. It's not inequality, it's an inequality. And this is quite specific for that. Okay? Well, this is the general expression of dissipation. Now, let me just say that we are going to consider here in general that we are, just for simplification, that we are in infinitesimal deformation, infinitesimal strain. Okay? Infinitesimal strains imply some hypothesis, maybe you should be familiar with, that says typically that the displacements are small, and the gradients of displacements are also small. Okay? So that means that, of course, infinitesimal, if I just deform that way this book, that's not infinitesimal strain. Okay? But if just consider this table and just consider the formation due to my weight, the displacements are very small. Okay? So that's the formation, the small strain. Displacements are small and the strains are also small. That is the infinitesimal strain theory. It can be proven also that infinitesimal strain, the density, which in principle can change along time. Of course, if I just, compress the air inside a domain, I can change density, but not with infinitesimal strains. Infinitesimal strains, as a consequence, imply that the density is constant in time. So we can consider non-homogeneous bodies with different densities in different points, but for every particle, the density is always the same. Okay? So that from now on we'll use the term rho zero to indicate the initial constant density at every point of the body. And the second consequence of the infinitesimal strain theory is that the rate of strains are now equal to the differentiation with respect to time of the infinitesimal strains. Maybe you can recall that in general, in continuum mechanics, we have different definitions for strains. The Lagrangian strains, the Eulerian strains, the different and infinitesimal strains. Epsilon will stand always for the infinitesimal strains, the symmetric gradient of the displacements, and in that case, it can be proven that the rate of a strain tensor coincides with the derivative with respect to time of the strain tensor, the infinitesimal strain tensor. Okay? Okay, under these equations, then we can replace that. Instead of rho, we have rho zero, so that's not an unknown, that's something that we know. And d is the rate of a strain. Okay? And this is the form of the dissipation equation that we are going to use in the following. Okay, so this is some preliminary. And I think it's a good point to stop, unless you have any question. Have any question? Is it really, I try to explain it simply, but I know that it's not, if you're not familiar with that, important here is that this equation here, this equation here comes from something, expresses something. This expresses, after all this manipulation, that the dissipation at every point, at every body, at every time, has always to be greater than zero. Okay? And that's the equation that is the part of the first building block or theory for constitutive modeling. Okay? Questions?